my doctoral thesis is entitled Security Automation in Software-Defined Networks. So I organized my presentation in these sections. First, I'm going to introduce the problems and my proposed solution. Then I will introduce fundamental concepts and state of the art. After that, I will provide some details about the intrusion detection system, then the framework that contains the reinforcement layer-based DDoS attack mitigation. After that, I will review the proactive defense with the software-defined networking and network function virtualization. And the experimental evaluation of the framework is presented in the section 6. And finally, I will draw some conclusion and future work. You can see here that this presentation is organized in the same way that was organized my thesis document. So let's start with the introduction. So I think that there are three main problems in securing networks. The first problem is that security is hard to manage because of the growing complexity of computer networks. So these networks appear that are called next generation networks. For example, the Internet of Things, the cloud computer, the vehicular communication, and 5G wireless communication networks. These networks are providing connections for new users, are providing also new services, new speeds. And these new devices connected in these networks are heterogeneous, which means that, for example, in the Internet of Things networks, each group of networks has a different network protocol. So it's going to be hard to manage the security in these networks. In our study, we focus in the denial of service attacks because these are probably the worst attacks for networks. So what we have seen is an increasing of frequency and complexity of these attacks, especially on the pandemic. We saw almost an exponential increasing in the frequency of the DDoS attack. And also in terms of complexity, we have seen here that the most basic attacks use only high volume of traffic. And from the point of view of network monitoring, these attacks are easy to detect. However, these new attacks of low-rate DDoS attack use low rate or low volume of traffic. So from the point of view of network monitoring, they are very hard to detect. And the last problem is that the current solutions are partially automated, which means that they only automate the detection of attacks. However, in this case, the network administrator neglect most of these alerts that are given by this automated intrusion detection. So even if they have the security solutions in place, the reason is, of course, that the huge number of security alerts produced by this system. So the idea is that not only the intrusion detection is automated, but also the mitigation. So that is our proposal, is to design and implement an SDN-based security framework that integrates artificial intelligence mechanisms for the detection and mitigation of complex DDoS attacks. So our proposal is that this framework is automated, scalable, modular, and flexible. And we are basing our design in this paradigm of software-defined networking. So some fundamental concepts of this and the state of the art of our study. First, I will define the software-defined networking, which is a fairly recent technology. In this technology, the control of the network, the control and monitoring of the network is centralized. And that is different from the conventional networks where the control is managed in a distributed manner. So each device has its own control plane. When we centralize the control plane, what we achieve with software-defined networking is reconfiguration of the network in real time. So we use this feature of reconfiguration of the network to apply on-the-fly mitigation solutions for networks. So I perform a comprehensive review of the state of the art of different methods searching for network defense automation with the SDN technology. So actually, I spent more than 1 year doing this research, and due to the time of this presentation, I can only present these main results of this study. What I found is that there are two main groups of defense. The one is the reactive, and the other group is the proactive defense. The reactive defense are those mechanisms that need two steps. They need first to detect an intrusion, and then they respond to those detection. And in the case of proactive mechanisms, they try to prevent an attack, and they do that by modifying the components in the network to harden attacks. So you can see here in this image that while the complexity of these mechanisms that we have found of reactive and proactive defense, while this complexity also increase the level of self-management or level of automation of these mechanisms. So we can find here some common mechanisms, for example, machine learning, deep learning, reinforcement learning. And on the proactive defense, we found here other mechanisms that are more common on next generation networks. For example, network slicing is a common application on 5th generation networks, also blockchains and network function virtualization. So our proposal was based on this review of the security of the state of the art. So we propose to combine reactive and proactive defense. So our idea was to that our mechanism respond to an event of attack, but also try to prevent attack. So we combine these two components. From this image, we use deep learning to detect attacks, reinforcement learning to provide responses to the detected attacks, and we use moving target defense and network function virtualization to generate a proactive defense in our system. So let's start with the intrusion detection system. So here we have two main components. The one is the monitoring model, and the other is the intrusion detection system that uses machine learning and deep learning to detect attacks. So in this design, the monitoring of the network is centralized in the controller. The controller captures the packets from the network and uses this application of SigFlow Meter, that is an application from the Canadian Institute for Cybersecurity. And using this application, we obtain some network flows that are identified by these 5 parameters: the source IP, destination IP, source port, destination port, and protocol. And for each of these flows, we have 76 features that can be used by the machine learning and deep learning to predict if there is an attack or if there is not an attack. So the studied attacks are transport layer attacks and application layer attacks. On the transport layer attack, we have the DDoS attacks that use protocols from the application layer on the TCP IP stack. In the case of the application layer, they try to use protocols from the application layer. And what we need to know from here is the application layer attacks are more recent and are harder to detect than the transport layer attacks. In the case of dataset used to train the machine learning and deep learning models to detect attacks, we use the SIG DDoS 2019 and SIG DDoS 2017, which are also from the Canadian Institute for Cybersecurity. And here we can see all the attacks that we are trying to study. On the the classification models used are from machine learning, random forest, super vector machine, and k-nearest neighbors. And from deep learning, we studied the multi-layer perceptron, convolutional neural network, long short-term memory, and gated recurrent units. So we can see that we evaluated a high number of mechanisms of machine learning and deep learning. Here we have the results. This was the first part of our study, the first results of our study. We defined some metrics that are defined here on the right, and what some important outputs of this analysis are that in the first place, we can see that the performance on the SIG 2019 dataset is higher than the performance of the models for the attacks in the SIG 2017 dataset. That is, of course, because these attacks on the first group of these first groups of attacks are easier to detect than the other groups. And also, we can see that we defined two metrics, the binary metrics and multi-class metrics. In the case of binary metrics, we only analyze whether the mechanism of machine learning or deep learning is able to differentiate if the traffic is an attack or not. Okay. In the case of multi-class metrics, what we analyze is if the mechanism is able to differentiate which class of attack we are obtaining. So of course we are gonna have that the binary metrics is one binary matrix of a specific model is always superior to the same metrics when we analyze the multi-class metrics. So another important output from this study is that the GRU and the LSTM methods provided the best responses. So we decided to continue the design of our framework using the LSTM method. So overall, the accuracy using dataset is higher than 99%. So here in this section, I will present the first version of the framework that tries to automate the detection and mitigation of DDoS attacks. So as we have already decided or selected a deep learning model to detect attacks, here we have this in the intrusion detection system, we have that deep learning models that will be used to classify or to find the attacks from the network. But before that, we have here a flow collector that is seen that collects the packets from the network and use SIG-flow meter, performs feature selection and filter the flows before these flows reach the intrusion detection system. In the intrusion detection system, we have also another pre-processing mechanisms. For example, here the principal component analysis. When the intrusion detection system detects an attack, it reports to the intrusion prevention system. The intrusion prevention system produces the responses for the detected attacks. This intrusion prevention system uses deep reinforcement learning to select the best action to perform for a given attack. But this intrusion prevention system produces high-level policies, security policies that should be translated to rules that will be installed on the network devices. So here, the flow rule manager is in charge to translate those policies of the intrusion prevention system to flow rules that are installed on the network devices. And also this flow rule manager connects or communicates with other applications in the network to avoid collisions when they are installing flow rules in the network. So what we achieve with this framework is an automated response that is actually is a reactive solution that is automated that detects complex DDoS attacks. So we achieve also, or we wanted to achieve with this framework, scalability. That is why we consider here some pre-processing methods. And also we can see here that we only use 30% of the total flows collected from the network to be used by the intrusion detection system to detect attacks. So we also keep the monitoring on the data plane, which means that we could perform the monitoring from this using the network operating system, using the controller. But the idea is that the controller has other activities to perform, so we need to release the activity of monitoring by using an external module that is located in the same data network. So let's focus on the reinforcement learning. When we talk about reinforcement learning, we need to define three main concepts. Four main concepts: the state, the actions, the reward, and the method of learning. In this case, we define or we model the system for a bidirectional connection between a host A and a host J. So for that bidirectional connection, we define a state. So the state is defined by a parameter D, which takes the value of 1 if there is an attack, and 0 if there isn't an attack. And there is another parameter M, which defines how harmful an attack is, and a last parameter, which is the bandwidth utilization. In the terms of action, we have these three actions: block the bidirectional connection, release that connection, and no actions. Of course, some of these actions, for example, block action, has a higher cost than the third action, which is no action. In terms of reward, we define this reward, and we have in this reward some hyper parameters, which we produce the values of these hyper parameters using experimentation. Finally, in terms of learning, we use Q-learning. As you may know, Q-learning uses a Q table that the Q table that maps for each state, which is the proper action. So this table is learned by using this formula, where we have some parameters that we need to set. However, we cannot use a simple Q table because we have an infinite number of states, because we here have this parameter M that is a real value between 0 and 1. In this case, we use deep reinforcement learning that learns that mapping of states to the proper action. In the experimental part of this first version of our framework, we obtained these interesting results. We simulated a data center topology that has 2 spine switches and 4 leaf switches. And we also simulated a high number of servers that act as legitimate user or attackers. And we only consider in this experimentation only one victim. So there are many attackers, but only one victim. Here we have some results for the detection rate when we use this simulation. We experimented for 1 attacker, 4 attacker, and 24 attacker in these images here in ABC. So overall, we can see that the average detection rate is higher than 98%. So we can see here a decreasing of the detection rate, because using dataset, we achieve a high detection rate higher than 99%. But of course, we will face more challenges when we deploy our methods to be executed on real time. So we will see this reduction of the detection rate. In terms of the response time of our solution, we here measure the response time of our solution for the same numbers of attacker. For one attacker in figure A, in figure B, 4 attacker, and in figure C, 24 attackers. We can see that we also varied the attack rate for each number of attacker. Maybe the main output of this experiment is that, as expected, we see that if we increase the number of attackers, the response time also increases because it's going to be harder for the intrusion detection system to detect multiple attackers, and therefore our solution of mitigation will take more time to respond to those attacks. To be more specific on how was the response time of our system, we analyze this. We propose this analysis where we propose a threshold of the response time to 30 seconds. So what we said here is that if our system, if our mitigation system has a response time higher than 30 seconds, we consider that event as a failure. So we can see that here for one attacker and for attacker, the response time is lower than 30 seconds, and for 24 attacker, the response time is higher than 30 seconds. We can see here this information here in figure C that the response time is higher than 30 seconds. Nevertheless, this doesn't mean that our system fails when the number of attackers is increased to 24. It only means that the response time is higher than 30 seconds. Here in this part of our study, we included the proactive defense, which means that we use the network function virtualization to improve the performance of our framework and also to improve the scalability of our framework. So here is the new framework where almost all the elements are the same, including the intrusion prevention system that uses reinforcement learning, the intrusion detection system that uses deep learning, the LSTM neural network. And here only we include, or the new element in this architecture is the moving target defense that use a network function virtualization. So the idea of using moving target defense here is to improve the responses of our solution in this way. So I'm gonna explain here one important thing, that the moving target defense here is another action that was included in the design of the reinforcement learning method. Here we have that the intrusion prevention system has these two actions, and through the moving target defense model, we provide another action, which is of course the moving target defense. And the moving target defense uses statistics from the network to process, to decide some important aspect that I'm going to explain in this slide. The approach of the moving target defense that we use is to migrate traffic. So the idea is that if we have if we initially have the host one communicated with the original server, we can deploy other servers that are known as shadow servers. These shadow servers have the same applications of the original server, but we can give to these shadow servers less resources. So we can migrate the traffic from the host one to these new shadow servers. So there are three questions that we need to solve in this mechanism. Question A is which traffic do we migrate? Question B is when is the traffic migrated? And question C, where is the traffic migrated? In order to achieve the security that we are trying to produce here, is the workflow of the moving target defense. So the two first questions given here, which traffic to migrate and when is the traffic migrated, is answered by the intrusion prevention system. So the intrusion prevention system triggers the moving target event. The actions that the intrusion prevention system takes are produced using our reinforcement learning mechanisms, as in the first version of our framework. When the intrusion prevention system triggers the moving target event mechanism, it has to produce the traffic migration. So for that, it uses the path statistics and select the decayed shadow server and then redirect the traffic. So if initially there was a communication between the host and the server, now the communication is between the host and the shadow server. So here we have to define how the moving target defense select decayed shadow server using path statistics. So this process is done using this method where the moving target defense use the path cost between two final nodes, and the path cost contains, of course, statistics for each link in the path. And the link of the path considered are the link utilization rate and the link delay. And the final formula to select the decayed shadow server is given by this definition of probability. So you may note here that the shadow server with the lowest path cost has the highest probability of being selected to migrate the traffic. So you can see that here the moving target defense used the statistic and decided where to migrate, whereas the intrusion prevention system decided when to migrate traffic and which traffic is migrated. Okay, and to achieve more scalability in our system, we reduce the number of states that we have initially in our first version of our framework to a limited number of states here. Here we only have 4 states. Therefore, we can use only the Q-learning using the Q table. So here, of course, the action were changed also because we integrated here the moving target defense mechanism. And how we did the reduction of the number of states is by simply setting a threshold for the continuous variable m. So we have this continuous variable now be as a binary variable now. So it's true or false, or 0 or 1 as you want. So here the reward function is defined in terms of the cost actions. Of course, as you might think, the moving target defense has the highest cost because it has to perform a lot of processing of data and perform some calculations. So the cost of the action for MTD, which is the action 1 here, is the highest. So this is also an hyperparameter that we need to choose using experimentation. And to perform experimentation, we set up this topology where we have 2 attackers, 2 legitimate users that are trying to connect to the original server that is placed in the switch 4. And we also configure 2 shadow servers that are deployed using Docker technology. It's important to notice here that we use Docker technology because because this technology allows us to deploy these servers whenever and wherever we want in this topology. I present here only one result of our experimentation where these 2 legitimate traffic are communicated with the original server, and only the attacker 1 is trying to attack to the server. So we see some states, some actions, and the reward. So the idea is that the reward is maximized by the agent, by the reinforcement learning agent. At the beginning, we can see in this reward function that we have a high value, and that is because at the beginning there is no attack. So the state of no attack has the highest value. But once the attack is detected, we see the reward function goes to the negative values. And after that, we need the agent to perform the correct action to to achieve the highest value of the reward. For example, here, when there is attack here, we see that the action of the reinforcement learning agent is action 2, and action 2 here is block the malicious connection. Okay. Experimental validation. We consider that it was important to validate our framework using physical devices. For that, I did a research study at the University of the Basque Country in Spain, where they have this laboratory of a smart network for industry, where they have all the SDN equipment, and we use only some of those equipment to deploy this topology that has the topology of a data center. So we can see here that there are two physical switches acting as the core switches, and we have here 4 leaf switches that were virtualized using a single physical switch. And we have here another virtual switch that is in charge to monitor the traffic from the network. The traffic monitoring application is here in this server, in this micro server, and it collects the features of the traffic, pre-process, and sends this traffic to the intrusion detection system, which is hosted here in this physical device. And also in this physical server is installed the intrusion prevention system, which provides the responses to mitigate the attacks. So these responses are sent to the ONOS controller, where is the application that translates the decisions of the intrusion prevention system to rules, to flow rules that are installed on these devices in the network. So we use here some microcomputer and microservers acting as legitimate user or attacks. And in the traffic, we use FTP, video streaming, HTTP, and we use this tool of slow HTTP test to produce the attacks. The contribution of the results of this research state and the experimentation are 2. The one is the data set that we produce and we publish, so new researchers can design and experiment their own intrusion detection system. And also, of course, we provided the analysis of the response of our framework for different number of attackers and victims. In the same way as the experimentation with simulation, we have here the performance of our solution is reduced when we increase the number of attackers and victims, because, as I said before, it's going to be harder for the intrusion detection system to detect on time if the number of attackers and victims increase in the network. So to conclude our study, the SDN technology, the software-defined networking technology, is at the core of the next generation networks, such as IoT, 5G, and beyond 5G and 6G wireless communication network. So providing the security to these SDN networks is the key to guarantee the correct performance of these next generation networks. And some results of using benchmark dataset demonstrated that our solution achieved 99%. And from this study serve to choose which is the best method to be used in our framework, in the final version of our framework. So the LSTM method presented the best responses. So we use this method in our framework. In terms of the intrusion prevention system, when we deployed our system in simulation, we saw this reduction on the precision on detecting attacks. So we have 99% when we use a benchmark dataset, but when deploying on simulation, we have this slight reduction. And that is mainly because, as I mentioned, our framework uses only 30% of the total flow that is captured from the network. So of course, if we have less information, we're gonna have less performance of our intrusion detection system. And when we include the network function virtualization technology, using this mechanism of moving target defense, what we achieve is that the legitimate traffic affected by the false positive rate of the intrusion detection system is migrated to the shadow servers, and the legitimate connections remain active. So, and finally, in the using in the experimental validation using the physical devices, we achieve accuracies between 81% to 90%. So you can see a reduction with respect to those results using simulations. However, our solution presented a high performance because we achieved a mitigation efficiency between 91% to 100% when we tested with different conditions for the number of attackers and number of victims. So notice that the intrusion prevention system is robust to the errors of the intrusion detection system, especially to the errors of false positive, all the false positives. The contribution of our study are 5, and we can summarize in 5. The one is the security framework that is automated and that was evaluated using extensive experimentation in simulation. And the contribution 2 is that we provided the open source, the source code of a prototype or a framework, which is in my personal repository in Github. So researchers can use or test or improve the proposed framework. The physical assessment is also, of course, a contribution of our work because using dataset, we can produce high results, but the important thing is that we can deploy our system in a real system, and we can test and calculate the results of our proposed framework. And also the datasets are published or were published, and this dataset was published in this repository of IEEE Dataport. And finally, we achieved some publications. We wrote 5 manuscripts, and we wrote actually 5 manuscripts, and the 4 manuscripts are already published on top journals. So you can see here which are the publications. For each step in our methodology, we produce a manuscript, and we actually managed to publish all this written manuscript. So, for example, for the review of the state of the art, we produced a survey paper published in 2021. For the framework that only includes the intrusion detection system, we published this paper that presents the comparison of diverse machine learning and deep learning models by solving or to detect transport and application layer attacks. When we include the intrusion prevention system using deep reinforcement learning, we also produce another manuscript, and that was published in the Journal of Network and Computer Application in 2022. And this 4.1 is still in process of review, and this contains the introduction of the moving target defense to the architecture to improve the performance and the scalability of our solution. And these 5, this last step in our methodology, that is the experimental validation, we also published a paper that was accepted actually the last week. And the diffusion, in terms of diffusion, we have presented the results of our study and the LACNIC event in Merida last week. I have also produced other manuscripts and published in collaboration with other members in our research group. For future work, we think that we can achieve more scalability by adding programmability to the data plane which means that the responses, the detections and the responses to this attack can be performed by the network devices. So we don't need to capture the traffic and go and process all the information in other models. We can perform this process in the switches, for example, using this P4 technology. We use also one controller in all of our experimental validations. So we could use more controllers to achieve more scalability, to improve the response time of our system. Finally, we think that the performance of detecting and mitigating attack could be achieved if several systems collaborate to detect and to prevent the attack. However, the owners of those systems won't be happy on sharing the data because they have some concerns about data privacy. In this case, the federated learning helps us to keep the data privacy. So this is considered for future work. Here I present some of the most important references like I consider in our study. Of course, my thesis document contains more than 250 references, I think. But I think that these are the most important that I consider in this presentation. So if you have any question, thanks for your attention.
Okay, thank you, Marcelo. So let's proceed with the questions. I'm going to give the opportunity to ask questions according to the way I see them in Zoom. So